Hello guys and welcome again to my channel. In the previous video we were dealing with the gas diffusion control of a heterogeneous particle-particle reaction in the SCM model, shrinking core model. Today we will be dealing and we will do the same thing by deriving the conversion time and the total conversion time of the spherical particles in the case of the ash layer diffusion controls and the chemical reaction controls. But before we continue, don't forget to subscribe to the channel and like the video. Also, if you didn't watch the previous video, make sure to watch it because some concepts will be directly related to the previous video. Now to begin, we said before in the gas diffusion controlling step that because the gas diffusion was controlling, the concentration gradient was along the gas fan. In the same manner, since the ash layer is controlling here, then the concentration gradient will be along the ash layer boundaries. So if we look at the concentration profile as function of the radial position, we see a constant concentration in the gas film, which is equal to CAG. And CAG is the concentration of A in the bulk gas. And I say gas this time and not fluid because we'll be dealing with gas solid systems and not gas liquid systems, and I will later tell you why. Then we see a huge drop in the concentration in between the boundaries of the ash layer as it's the controlling step, and then we see a zero or constant in the unreacted core, which is the chemical reaction step. Now we will be defining some notations that will be helping us in order to proceed with the calculations, which are the fluxes of A. The flux of A that will be entering through the exterior surface of A will be denoted as QAS. The one entering through any surface of radius R, you can see here it's the dashed one, it will be denoted as QA, and that entering through the surface of the unreacted core is QAC. So, I told you we were dealing with gas-solid system. The reason behind that is in order to simplify the mathematics. Because we can make the assumption of the steady state, and in reality it's a pseudo-steady state assumption, because in gas-solid system the shrinking rate of the core is much slower than that of the diffusion of A through the ash layer. This relates to the difference in the densities in between the gas solids, which can reach up to a factor of 1000. However, in the liquid-solid system, the difference in between the densities of the liquid and the solid is much smaller and not that huge, and thus making the assumption of a pseudo-steady state condition is not reasonable. So we'll be treating the simple case, which is the gas-solid system, instead of going into a complex mathematics. In the first line here, we see that what is written here, that this again QA, as we said, it enters through any surface of radius r for pi r squared. This is the surface. QAS, which enters through the exterior surface, this part, so multiplying by the surface and multiplying by the unreacted core for QAC, and equal to constant. So why is that? The reason behind writing this equation is, try to think about it like hydraulics. You know that the inlet flow rate or inlet flow is equal to the exit flow. So if you go back to what you saw in the previous slide, a QAS was entering and it was leaving. This that was leaving was entering through the surface of any radius, which is QA, and was also this QA that was leaving was again entering into the unreacted core. So it's like the inlet, the outlet is the inlet for the other surface, and thus we equated them. I think this is the most simple way to think about this equation. Now for QA, we will be dealing with this QA for any radius in order to make the derivation. This equation comes from fixed law, so we are assuming that the flux of A through the ash layer is given by fixed first law in the radial direction along the radius, where dE is the effective diffusion coefficient of the gas in the layer. So replacing for dE times dCA over dR in this equation, in this part, so we have minus dNA over dt will be equal to 4 pi r squared times dE times dCA over dR which is equal to constant again. Now we will integrate for R and dCA, as we'll be proceeding with two steps integration. Now we leave the factor minus dna over dt outside the integral, and we'll be integrating only for dr and dc. Again, as we said before in the previous video, that you might be lost while we are integrating from R to RC, and so it's from the largest to the smallest. Again, don't forget the negative sign here, that will change everything. Now it's just an arrangement and simple integral. The integral of 1 over r squared is minus 1 over r, and replacing again, it will be a 1 over rc minus 1 over r. And the integral of dCA will be equal to CA. In fact, it's CA, which must be 0 minus CAG, but the sign was exchanged with this side. So we end up with this equation until now. Now what we will do is the rearranging of the previous equations, and the trick that was done here after the rearrangement, the D and A was changed as exactly as we did in the previous video. It was just by equating D and A equal to B, D and B equal to B D and A from the stoichiometry, and replacing for D and B by rho times dV, where D equal 4 over 3 pi R3. So it's just the same procedure as before. I don't feel like redoing it because it's more like repetition, and it's better that you get used to such equations for your exams because you have to get used to what is happening in the equations. Now, integrating on both sides, the integral of 1 over rc is minus 1 over rc squared. The integral of 1 over r is a constant, but oh sorry, there is an rc squared here, so it's like we are integrating rc minus rc squared over r. So the integral of rc is rc squared over 2, and the integral of rc squared is rc3 over 3r, because r is a constant with respect to this integral. And just applying the boundary conditions and on both sides and rearranging to get the time for the conversion, we get the following equations. And then to calculate the time for the complete conversion implies there's no more unreacted core, and RC will be 0, and this term and this term will be 0, and we will end up with tau is only equal to this term. Now, if we divide these two by each other, so t over tau, this term and this term will be neglected, and we will be left with the term in the brackets. And this is what really is written here. T over tau is equal to 1 minus 3 rc over r squared plus 2 over rc over r cubed. Now, if you remember in the previous video, we were dealing with when we were deriving t over tau as function of the conversion of xb. We showed that 1 minus xb, which is the fraction that has not reacted yet, was equal to rc over r over 3, and just the replacement was done here to get the equation as function of xp. Now for the chemical reaction control, so I think now you got used to it. Now you must predict that the concentration gradient will be along the unreacted core in the reaction surface. So you see it's constant, and then whoop, it drops until 0, because from CAG equals CAS equals CAE till 0, because the reaction step is the controlling one. So what we are doing here, the variation of A with respect to time, but we are dealing with respect to surface of the unreacted core, because the reaction is occurring at the unreacted core. This is a small, okay, here there's, it's dNB, this must be dNB, and this is dNA times B from stoichiometry. Okay, it's equal to the rate of the reaction. We are assuming a first order reaction, so it's equal to B K double prime CAG. B the stoichiometric coefficient again. K double prime is per unit surface, as we are dealing here per unit surface. So K double prime is the kinetic constant per unit surface. Again, Rearranging in the same concept, we just do a rearrangement and we integrate. But before the rearrangement, we also do DNA is equal to B, D, and B. So here is B and here is A. I'm sorry again. D and B, and B is equal to rho times dV. That's equal to rho times dV. V is equal to 4 over 3 pi R3 and derive 4 over 3 pi RC, derive power 3, and then we can derive it the same, totally the same we are doing. So after doing the gas diffusion controls, it must always seem like a repetition for you what we are doing for the chemical and the ash layer diffusion controls. And that's also a small rearrangement, then integrating from R to RC. Don't forget the negative sign, not to get lost. And then integrating 4T, and then the value after rearranging 4T, we get this value. So we get tau is equal to rho B R over B K W prime CAG from equating, because tau is the time for the complete conversion, which means RC equal to 0. This term will neglect. We will be kept with this term only. And thus T over tau will be deriving this term by this term. So all this part here except for the R will be cancelled, and we will be left with or we can take R as a common factor, and we'll be left with 1 minus RC over R. Again, 1 minus XB equal to RC over R cube, and thus RC over R will be 1 minus XB to the power 1 over 3. And this is the time or the equation that relates the time and the time for the complete conversion when the chemical reaction controls and the shrinking core model.